Hello friends, I welcome you in lecture number 51 on Laplace transform. In this lecture we will discuss this question on finding the Laplace transform, and this question was asked in GTU Winter 2019 exam. The function given is discontinuous function. Function is different in these intervals. In 0 to k, value of function is t divided by k, and in k to infinity, value of function is 1. And we have discussed in earlier lectures that whenever we have this type of discontinuous function, we can first express it in terms of unit step function, and then we can apply second shifting theorem to find out the Laplace transform. So first we write given function in terms of unit step function. Here first interval is 0 to k, so endpoints of this interval are 0 and k. So we consider the difference of unit step functions at these two endpoints. Unit step function at first endpoint, which is 0, minus unit step function at second endpoint, which is k, and we multiply this difference by value of function in that interval, and it is t by k, plus we repeat this same process here. Here interval is having endpoints k and infinity. T is greater than k, that means t lies in the interval k to infinity. But we are not considering infinite endpoint, we consider only unit step function at finite endpoint, which is k here, and value of function in this interval is multiplied with this unit step function at k. Now we simplify this. This we can rewrite as t divided by k, unit step function at 0, minus t divided by k, unit step function at point k, plus 1 times unit step function at point k. And in the next step we will take u of t minus k common from these two terms, and we rewrite our function t by k u of t minus 0 plus 1 minus t divided by k times u of t minus k. And we can simplify further also. This is t divided by k u of t minus 0. This I can write by taking k LCM. I can rewrite this as k minus t times u of t minus k. So we are able to express given function f of t in terms of unit step function. Now we apply Laplace transform on both sides, and for that we will apply second shifting theorem. First we write down that Laplace transform of f of t will be equal to Laplace transform of t by k times u of t minus 0 plus Laplace transform of k minus t divided by k times u of t minus k. And now using alternative form of second shifting theorem, if we recall the alternative form of second shifting theorem, it says that if our function f of t is multiplied by a unit step function at point a, then this Laplace transform is equal to e raised to minus as times Laplace transform of this function after we replace t by t plus a. So whatever function is multiplied with unit step function, in that function we have to replace t by t plus a, and we have to find out Laplace transform of that function, and that Laplace transform is multiplied by e raised to minus as. So for the first part, value of a is 0, so we write e raised to minus as, that is minus 0 into s, and in this function we have to replace t by t plus 0. So for understanding we are writing in this way, t plus 0 divided by k, and we have to decide Laplace transform of this. Same thing we apply here. Here unit step function is at point k, so we consider e raised to minus ks, and in this function we replace t by t plus k, and then we find out its Laplace transform. So k as it is, this t is replaced by t plus k divided by k. So Laplace transform of this function when we replace t by t plus a is value at which unit step function is written. Here unit step function is at a equal to k, so we replace t by t plus k, we keep other things as it is. Here value of a is 0, so we replace t by t plus 0. Now e raised to 0s is 1, and using linearity property, this we can rewrite as 1 by k times Laplace transform of t. Same thing we can do here also. We can take this k common, 1 by k outside using linearity property, and if we consider this negative sign inside the bracket, we have k minus t minus k. So k will cancel out and we will be left with minus t. So this is 1 by k. Laplace transform of t is 1 divided by s square. Laplace transform of minus t is minus of Laplace transform of t, e raised to minus ks divided by k as it is, this negative sign outside, into Laplace transform of t, which is 1 by s square. So finally we obtain 1 minus e raised to minus ks divided by k into s square. 1 minus e raised to minus ks, we can take this k into s square as LCM. So in this way we can decide the Laplace transform of a given function using alternative form of second shifting theorem together with unit step function. First we have represented our function in terms of unit step function, and then we apply alternative form of second shifting theorem. Okay, fine. So this is one way of obtaining Laplace transform of this function. If we wish, we can use the definition of Laplace transform also to write down the Laplace transform of this function. Here nothing is specified. They have not specified that either use definition or unit step function to obtain the Laplace transform. So you can apply definition or you can use second shifting theorem together with unit step function to obtain the Laplace transform. For our surety, we are doing this same problem using the definition of Laplace transform also, and we will check whether answers are same or not. So for that, first we write our function again. F of t is t by k if t lies in the interval 0 to k, and value of f is 1 if t is greater than k. So now we go by definition. By the definition we can write that Laplace transform of f of t is equal to improper integral from 0 to infinity e raised to minus st f of t dt. Now here function is different in both the intervals, so we have to break our interval of integration into two intervals, in 0 to k and in k to infinity. In 0 to k value of function is different, and in k to infinity value of function is different. So using the property of integral, this I can rewrite as integral from 0 to k plus integral from k to infinity. In 0 to k value of function is t by k, so here we put t by k in interval 0 to k, and in interval 1 k to infinity value of function is 1, so here we write 1. Now here 1 by k is independent of t, so that we can take outside, and we apply integration by parts. We consider t as it is. Integral of e raised to minus st is e raised to minus st divided by minus s minus derivative of t into integral of e raised to minus st divided by minus s. Integral of e raised to minus st is e raised to minus st divided by minus s, and there is already minus s in the product, so we will have 1 by s square, and in the next step derivative of 1 will be 0. So we stop here. We have applied integration by parts with u equal to t and v equal to e raised to minus st. Here integral of e raised to minus st is e raised to minus st divided by minus s, and limits of t are from k to infinity. Now we put the limits for both the integrals. For this first integral, first we put t equal to k. So in this term, if we put t equal to k, we have k times e raised to minus ks divided by s minus e raised to minus ks divided by s square. This is for upper limit t equal to k. For lower limit, we have to put negative sign, upper limit minus lower limit. Value of this will be 0 for t equal to 0, and for t equal to 0, this term will be e raised to 0, that is 1 divided by s square, and there will be minus 1 by s square. So minus minus is plus. I write directly due to minus sign of lower limit, upper limit minus lower limit, and here we will have 1 by minus 1 by s square, so minus minus plus. And here if we put t equal to infinity, upper limit, we will have e raised to minus s into infinity, and this is going to be e raised to minus infinity if s is positive, and if s is negative, it will be e raised to infinity, that is going to be infinity, and that is not of our interest. We are interested in the finite values. So if s is positive, it is e raised to minus infinity, and that is going to be 0. So if s is positive, upper limit for t equal to infinity, we will have 0 if s is positive. For t equal to k, we will have e raised to minus ks divided by minus s, and minus minus plus. So for t equal to k, we have e raised to minus ks divided by s. Now we simplify this. We multiply this whole quantity by 1 by k, and we have e raised to minus ks divided by s minus e raised to minus ks divided by k times s square plus 1 divided by k times s square, and plus e raised to minus ks divided by s. So these two quantities will cancel each other, and we are left with 1 by k s square minus e raised to minus ks divided by k s square. And if we take the LCM, this we can rewrite as 1 minus e raised to minus ks divided by k s square. So this is Laplace transform using the definition, and we can compare this answer with our previous answer which we have obtained using unit step function. This is number 1. It is 1 minus e raised to minus ks divided by ks square. Sorry, this is number 2. 1 minus e raised to minus ks divided by ks square, and that matches with first method which we have done using unit step function. So you can understand same question can be done using unit step function as well as using the definition. But if they specify that find the Laplace transform using unit step function or using second shifting theorem, then you must use unit step function. If nothing is specified, either you can express in terms of unit step function or you can go by definition, and you can compare both the methods and you can decide with which method you are comfortable. So this is all about this session. I hope you like it. Thanks for watching.